All right, good afternoon. Let's work a problem in sugar chemistry. And this is a reaction in which an aldose, generically written like this, is converted into a ketose. As you may remember, in the individual series, the aldoses and the ketoses are isomeric. So, for example, glucose is an isomer of fructose. Okay? And as you can see, what happens formally is these two hydrogens get transferred over to the carbonyl function, and so this function gets oxidized, and this one gets reduced. Overall, it's an isomerization. Nothing is added. Nothing is taken away. And this works particularly well with on the basic solution. Now, sugars are reasonably sensitive, so this has to be carefully fine-tuned to work. And if you do it in the lab, under laboratory conditions, you use buffered solution. The pH is actually rather close to 7 when you do this. In nature, enzymes do this quite effectively. And industrially, this is also used. So how does this work? Let's do it just for the simplest sugar that we know, D-glyceraldehyde. And the first step is the base has to attack and do something. Okay? Now, base, in the presence of this, you can imagine various scenarios, one of which is, of course, deprotonating the OHs, and it will do that. And we'll do so reversibly. That's a reaction that doesn't go anywhere, so we don't have to worry about it. The second thing that will happen very fast is addition to the carbonyl. That's the first step in the hydration, and since this is done in aqueous solution, indeed, it leads to the hydrate. And again, this is also a dead-end street. It doesn't go anywhere, so this is sort of a background noise reaction that occurs in addition to the deprotonation here. But every now and then, it will deprotonate here. Okay? And the reason it deprotonates here, we can, you could have guessed that, that's the third position where we can lose a proton where the base can attack, because that is next to the carbonyl. And there's an additional help by the inductively electron-withdrawing oxygen, but it's enough to have the carbonyl there. These are conditions that we use for the aldol addition and the aldol condensation, basic sodium hydroperoxide, sodium hydroxide rather, that goes through enolate formation. So when you make this enolate, so let me write the carbon here. Then you write the electron pushing in this way, and so what you get is this enolate ion. And you can see already what is happening here. We're sort of symmetrizing these two carbons by putting a double bond in there. You write it like this. And typically at this stage, since this is an aqueous solution, we would get reprotonation, and reprotonation on oxygen would give you the enol. But in this case, we can actually do this intramolecularly. So this is one of the rare cases where we're not protonating and deprotonating in case we have to shuttle protons from one place to another, which is typically a two-step process. Here we can actually write a 5-member transition state for the proton to transfer, and that's faster. Oops. And once you've done that, we now have the enol function up here. And the enolate here. Oops, running out of space, and that one cutting out carbons. Let me do it over here. And now all we have to do is protonate with water over here. And so this goes by attacking at that carbon, and that generates the CH2OH up here, and the carbonyl function, and the CH2OH here, and that's the hydroxyacetone. And so that's the ketose, the keto triose isomer of D-glyceraldehyde. There are two things that are interesting here. One is this is a general reaction, so you can isomerize aldoses with ketoses. The second thing is that in this mechanism, when you hit these aldoses with base, you're losing the stereochemistry at this carbon. So you can actually interconvert at this particular stereocenter, since this is reversible under certain conditions. But typically, this is run to isomerize over to the ketoses. And these reactions are almost thermoneutral, so typically you get equilibrium of these. And where this is important is in the so-called high fructose corn syrups that are much in vogue and much discussed in the literature, particularly the web, where people think that this is really bad for you and so on. And there is a little margin entry in your book that addresses this. There's a lot of misunderstanding that goes on here. So what is going on in reality is that one can produce glucose from starch, corn starch especially, so that's why they're called high fructose corn syrups. But any starch, you can do from potatoes, from spaghetti if you want, or from bread and so on. Okay? Because as you remember, starch is nothing else but polyglucose. So it's glucose molecules by the thousands, by the millions, linked by the acetal carbon oxygen bond with another carbon at the 4 position. So the acetal carbon makes a bond, an ether bridge, to the number 4 carbon of the glucose. And then the second glucose has an acetal oxygen, and it binds to another C4 oxygen of a third glucose, and so on. So there are industrial processes of turning starch into glucose. And that would be fine if one could use, well, one can use glucose, obviously, since it's saccharide, it's sweet, as a sweetener. However, public taste didn't like it because glucose is less sweet than table sugar. And now remember, table sugar is glucose attached to fructose, where the two acetyl carbons form a bridge. So you have a bis-acetal, a mutual acetylization of the two molecules. So in order to generate the sweet taste of table sugar, industry decided to use this process on glucose to equilibrate glucose with fructose, the ketose isomer. Okay? Now that process doesn't go beyond a certain percentage, 30% or 40% or something like that, maybe 30%. And so that still wasn't sweet enough. So in order to bring up the sweetness of that concoction to that of table sugar, they added fructose. And when you have a 1-to-1 mixture of glucose and fructose, that's called HFC50 or something like that, because it's a 1-to-1 mixture, that, of course, tastes exactly like table sugar, because, in fact, it is exactly table sugar. 50% glucose, 50% fructose. Okay? And so all that high fructose labeling means is that you're adding it so it is exactly the same composition as table sugar. So there's nothing nefarious about it, or nothing that is deleterious to your health, or you get some enormous excess of one particular compound. It's just table sugar, chemically. All right. So let's finish up heterocycles, heteroaromatics. And the last one we're going to look at is pyridine. Now, so far we've looked at heterocyclopentadienes, where we had a heteroatom with a lone pair, where the lone pair was donated into a 4 pi system of a diene, and that added up to 6 pi electrons, and this was aromatic. And we are talking about 5 atoms with 6 pi electrons, so these are electron-rich, very reactive in electrophilic aromatic substitution. There's another way of introducing a heteroatom into a fully delocalized pi system, namely starting with an aromatic system, and here we're just starting with benzene, replace one of the carbons with nitrogen. And so in the molecular model, this is what I did here, and you may recall this is exactly the same molecular model that I used for benzene, but one difference. Here I've taken away one of the hydrogens and replaced it with this lone pair. Okay? And so in this model, this atom here signifies nitrogen. And you notice that nitrogen is sp2 hybridized, as it should be. It's an imine type nitrogen. And here's the lone pair. The lone pair is not participating in the delocalization of the 6 pi framework. It's the p orbital of the nitrogen that has 1 electron that participates in the cyclic array, making this what one might call an azabenzene. Okay? So it's a derivative, if you wish, of benzene. 1 carbon has been replaced by nitrogen. Otherwise, the electronic structure looks very much the same. And if you focus on the CN double bond, it's really sort of like an imine. Okay? And an imine is the same thing. This lone pair does not interact with the pi frame of the double bond. This means that this nitrogen, since it's not donating its electron pair, is a replacement for carbon, and that replacement means that you're replacing an atom with something that's much more electronegative. That nitrogen is electronegative, and therefore it pulls inductively very strongly, and that makes this benzene ring, the azabenzene ring, much less electron-rich than benzene itself, with all its consequences, as we'll see in a minute. One can see this very nicely in the electrostatic potential maps. Here's benzene, I've lifted from chapter 15, and you can see, look at the top view, that there is a pi cloud above and below the plane of the benzene ring. It's deep red. Okay? So it's the ball of electron density. Now we look at pyridine, and I'm showing it sideways so that the pi cloud is up on top here, and the nitrogen is to the right. So you see that the proton is missing. And if you look at the top, you see this trough here. This is sort of the donut-shaped hole here, the donut hole. That's the pi cloud. And when you compare the colors, this is no longer red. Okay? It's fairly orange, yellow-orange. So much less electron density. This is done on the same scale of these potential energy map renditions. You can tweak your computer to make the colors contrast as much as possible. And what's up front here is the blue hydrogens. The hydrogens are always blue because they're almost always slightly delta plus, as also seen in the periphery of the benzene. But what's striking is out here, this lump that's sticking out, the red lump, that's the lone pair. Okay? That's in the plane of the 6-membered ring. And that's where a lot of electron density shows up, and that's just this lone pair here, which is just sitting there on an sp2 hybridized carbon. So the nitrogen withdraws electron density, and we can show this very nicely using resonance pictures. So you take pyridine, and you can do first the typical resonance, the typical benzene resonance by moving the 3 electron pairs around, 1 electron pair, second, third, that gives you this resonance structure. But then in addition, to highlight the electron withdrawing nature of nitrogen, we can write dipolar structures. Okay? And so you can make this electron pair move over to nitrogen, and that puts a plus charge on this carbon and a negative charge on the nitrogen, and accommodated by its relative electronegativity. And then this plus charge, of course, moves around by electrophilic transposition to here and to here, basically meaning that there is delta plus, relatively speaking, on these carbons. They're less electron-rich than in benzene. So here's again the molecular model, basically the model I've shown you there, but just on paper. And this nitrogen, you can see, is sp2 hybridized. The lone pair is perpendicular to the pi frame, and we have 6 electrons in a cyclic array. So the question now is, since this is a nitrogen with a lone pair, is this thing basic? And the answer is, yeah, it's basic, but nowhere near as basic as a normal amine. And the reason is simply, it's an sp2 hybridized carbon. It's got nothing to do with aromaticity. It's almost the same as an imine, or it's the same as an imine, or related to an imine basicity. Okay? So protonation occurs, you get pyridiniumine, and when you measure the pKa of the conjugate acid to pyridine, pKa is about 5.3. So it's less acidic than a carboxylic acid. It's more acidic than a normal amine, where the nitrogen is sp3 hybridized, and that can be ascribed largely to the fact that this nitrogen is sp2 hybridized, so it brings down the pKa by 3 or 4 units. Here's the pKa of a normal ammonium salt. So it's less basic than a normal amine, and that is actually often used in a practical sense by organic chemists if they want a mild base to soak up protons in a reaction mixture. For example, we have lots of reactions where pro-acid is generated. One example being all the reactions of acyl halides, starting with acyl halides and water. Okay, they make carboxylic acids and HCl. So if you don't want that acid floating around, you typically add a mild base. Carbonate would do, but often people add a soluble amine base, and this one is very good for that. It mops up the proton, and it's harmless because it's an aromatic compound. In fact, this thing is a liquid, commercial. It's used as a solvent, just like benzene is used as a solvent, because apart from its basicity, it's relatively unreactive because it's aromatic. So what sort of reactions can we expect? There are a bunch of reactions in the book. We'll just restrict ourselves to substitution, electrophilic as well as nucleophilic. Right off the bat, you can predict what will happen. The nitrogen is equivalent to a strongly electron withdrawing substituent, resonatingly withdrawing substituent. So we should expect much less reactivity in electrophilic aromatic substitution, and the nitrogen should direct to the 3 position, like meta, if we have an electron withdrawing substituent here. So the nitrogen is basically a surrogate for carbon-bearing nitro, let's say, okay? Something that's strongly electron withdrawing, which would direct electrophilic substitution here, and which would make it much harder to do an electrophilic aromatic substitution. And so indeed, for example, bromination occurs at the 3 position. And look at the conditions. They're really quite harsh. You use bromine, and H2SO4, SO3 means that you have concentrated sulfuric acid, no water, and you bubble SO3 through this until it starts fuming. So it's often called fuming sulfuric acid, a very vicious acidic mixture. And it's used in order to polarize the bromine-bromine bond such that Br comes off as Br minus. Very similar to Lewis acid. Remember, we use typically FeBr3. The FeBr3 pulled off Br minus, leaving behind the blue Br plus. In this case, it's the SO3 H2SO4 concoction that does this. So we have almost, not quite, but almost free Br plus that is necessary in order to pull this off. Okay? And then the yield is not too bad. So that can be done. But then you can look at the corresponding nitration, which was done here. I mean, you can do nitration with nitric acid. That doesn't work at all. In order to get some nitration, in this paper, they use sodium nitrate and fuming sulfuric acid at 300 degrees. Okay? Under these conditions, you get HNO3 and then NO2+. Okay? And you can get nitration at the 3 position, but notice the yield. It's a punk yield. Right? Terrible reaction. In part, the problem of this reaction and many other electrophilic aromatic substitution reactions on parent pyridine is that the nitrogen lone pair gets protonated. And so most of the stuff in solution is actually pyridinium. And that is even more deactivated than just pyridine, because now you have a positive charge that's pulling on the 6 electrons that are part of the electron sextet. So electrophilic aromatic substitution is slowed down because of that. So that's typically not very good. Doing reactions on the parent system is typically a bad reaction. So why do we get meta substitution? Well, you already know the answer, but I'm just going to repeat it. Basically, this is a review of chapter 16. If you think of this as an electron withdrawing substituent, if you attack at the ortho position or at the 2 position of pyridine, notice that the electron pair goes out, makes the bond to nitro, and that puts a plus charge on nitrogen. That's terrible. Okay? It's the same as putting a plus charge on a carbon bearing a nitro group or a sulfonic acid group. Okay? So that's a poor structure. The allylic transposition structure is okay, and this one is okay, although of course they're all sextets. If you do the same thing for the 4 position, or you can call it para position, then starting with an electron pair here, that moves out to the nitro, your plus charge here, allylic, that's okay. Allylic transposition, again, very poor structure, and this one is okay again. But if you go meta, that's the least bad option of the 3. You notice that the plus charge bypasses the nitrogen. So attacking here puts the plus charge here, and here you see the bypass jump, where the plus then by allylic movement moves over here and it moves here. So we have 3 reasonable sextet resonance forms, as opposed to only 2 for the other 2 possibilities. And so this is the one that wins out. Yeah. Now, by far more useful, actually, is when you have substituents on pyridine activating substituents, starting with just alkyl. Then electrophilic aromatic substitution starts working fine. And so, for example, this guy, 2,6-dimethylpyridine, HN nitration, is still 100 degrees in this paper, so you have to beat a little bit of this, puts the nitro into the 3 position fortuitously. It's really ortho to the methyl and para to this methyl. Okay? So the substituents take over as before as the activating substituents. You can ignore the nitrogen in the pyridine ring, just like we ignore deactivating substituents if you have an activator on the benzene ring. Things are actually much simpler than one thinks, right? As you probably noticed, once you have an activator, you just look at the activator and put it wherever the activator sends it and ignore the rest of it. Okay? Don't be confused. Don't over-interpret what's there. Okay? And this just happens to be also meta to this nitrogen. Here's another one. Amino substituent, of course, is great. That's a very strong activator, and this will be ortho-para directing, and the rules for ortho versus para still hold. This is Stericate Mohindet here, and so in this paper, they isolated 90% of the para material. They don't mention the ortho. I suspect there's some ortho, 5%, 3%, what have you. They didn't bother isolating it. Okay? So one can, and so this is a bromination. Notice they didn't even use a catalyst. They just used bromine and acetic acid at room temperature. So this is a pretty mild reaction because this is such a strong activator. You may remember that we said that activating phenols, for example, get brominated. You don't need a catalyst. But again, if you're not sure in your system, by all means, in all of your electrophilic halogenations, use iron chloride or iron bromide as a catalyst because it'll just go even better. It's not necessary, but it doesn't matter. So if you're not sure, put it in. The corollary of the nitrogen being electron withdrawing, making the pyridine ring electron poor, is nucleophilic aromatic substitution. And that works on pyridine quite well. And again, the rules are such that it's best if you're displacing substituents at the 2 and 4 position, similar to ortho-para positions in substituted benzenes, because the resonance picture of the anion that you get as an intermediate after the addition elimination put the negative charge on the nitrogen. So this guy, for example, with sodium methoxide, methanol, 75% of the para-methoxy or 4-methoxy pyridine. And this goes by the usual mechanism, so I'm just repeating what we did for nucleophilic aromatic substitutions, but now applied to pyridine, and I'm just putting in 2 leaving groups, but I'm attacking at the 2 position, at the 3 position, at the 4 position. So if you attack at the 2 position, where we have this leaving group, the electron pair